All right, good morning, folks. Good morning. Please take out your labs from the last time we were together on Thursday. Okay, you're going to need those materials for today's lesson. Can I hold this up, Will? Looks like this, okay, where we looked at the different polymers. Thank you. Got him, Zach? Got him, Leah? Got him, Nick?
This was ours, and then this is just everybody's, so you should probably just get ours and ours.
All right, if you weren't here on that lab day, please share. Please look at information from the other class or the other students at your table as we go through today's lesson. So let me go over the agenda first. We're going to do a quick review of what we've been learning. And our learning objective for today is what, Zach? Can you read it for us? Over there?
There. Objective, students will learn how to determine the approximate chemical structure of a polymer based on its physical characteristics.
Good, thanks, Zach. All right, we're going to do a little text annotations of the graphs and charts that you picked up today. And then we're going to meet the objective of determining the chemical structure of these polymers by looking at some of their physical characteristics. Okay, so last time we were together, we did a lab on polymers, but let's quickly review. Ryan, Perry, what is a polymer? All right, that's okay. Jillian, what's a polymer?
Is it like multiple monomers?
Good. Multiple monomers that are what? You're right.
I forget.
Multiple monomers that are what, Gio?
And a long chain.
They're long chain, so they're somehow linked together, right? Yeah. Okay, and so some examples of polymers. We've talked about biological polymers. An example of biological polymer might be what, Mitchell? Well? That's what I'm...
Not a monomer.
What are some monomers in biology from biology class?
Oh, they're amino acids?
Yes, amino acids, very good. And amino acids link together to make what kind of molecule? Anyone?
Protein.
Protein, thank you. Yeah, so that's an example of a biological polymer. Some synthetic polymers or man-made polymers. Ricky, can you give me an idea of what?
Plastics?
Plastics, yeah, exactly. And so we looked at some plastics and their characteristics the last time we were in lab together. And for example, this group over here, you guys studied a certain characteristic of a plastic or of a polymer. Do you remember what that characteristic was?
The branches.
The branches, right, exactly. And so what was the physical quality? That's the chemicals quality. What was the physical thing you tested?
Oh, plasticity.
Yeah, the plasticity, right. And this group here, what was the physical characteristic you tested?
Bridges of sulfur.
The what?
The bridges of sulfur.
No, the elasticity.
Okay, the bridges of sulfur. And so what, and that was the elasticity, right, exactly. Good, so we have these different characteristics that determine their structures. All right, so folks, what I want you to do is, let's move into today's lesson. Look at the graphs that you picked up today. So it's, looks like this. And we're going to annotate these and break these apart a little bit so we can use them in today's lesson to help us out. Okay, so I'm going to pull mine up on here. All right, so our first graph, okay, it says the effect of side chains on the plasticity of a polymer. Okay, so there's a lot of stuff going on in this graph. So you guys said you did this side chains, right, your group? First of all, let's circle side chains here. Because if you didn't do this test, you might need to have a refresher on what this means exactly. So your group over there, what does it mean by side chains? What is, so Jess, what does it mean for a polymer to have side chains? You don't remember? Do you remember, hon?
Like the branches.
Branches coming off the what?
I don't know.
All right, so folks, remember, I think we need a little recap on a polymer or what a hydrocarbon looks like. So what is a hydrocarbon? It's a molecule made up of two atoms. Zach?
Hydrogen and carbon.
Hydrogen and carbon, right. And so we learned a little bit how to name those hydrocarbons. So for example, you might draw a hydrocarbon like this. And you know that the carbon atoms are at each point of the line. Also here are, as Zach said, the hydrogen. So you guys in the back, you said you had side chains, right? So a side chain might come off one of the carbons, okay, and look like this. All right? So then you tested the plasticity of this. And so can you guys define, actually let's all say, that's one of our vocab words for the unit. So I'm going to say plasticity, and I'm going to signal for all of us to say it because it's kind of a weird word, right? All right? So plasticity. 1, 2, 3.
Plasticity.
One more time. Plasticity. 1, 2, 3.
Plasticity.
There we go. Thank you guys. All right, so what does plasticity mean exactly? Let's draw an arrow because we're going to define it. So you're going to need to look at your lab from last week. Okay, fine on. So look at this, guys. Somewhere on there you might have, or not that one, I'm sorry, the other part of your lab. It's the longer sheet where you wrote down, you collected group data. I think it's this one. This one here. Zach's got it. He wrote plasticity at the top because it's our first characteristic of a polymer. Okay? So everyone needs to have that one too for today. So your guys' group that tested plasticity, I know I keep picking on you. Nick, do you have the definition for plasticity?
Yes.
Give it to us.
The measure of the ability of an object to be molded or shaped without breaking.
All right, so guys, let's write that definition on the side here. So let's define plasticity. Okay, so the ability and this should be somewhere on your paper too, but I'm going to read it. So the ability for an object to be shaped or molded without breaking. So that's what plasticity means. And so this group was the expert on plasticity last time we were together. You guys have different, I know you guys tested the density, right, Leon? Okay, so let's on this side of the graph then, what is going on in this graph? So how, we know the IV, we have the IV, we have the DV. The DV in this case is plasticity. The IV is the amount of side chains. So what is the relationship here between the IV and the DV? So you guys all have the graphs at your table. Gio?
If there's a low number of side chains, then the plasticity is high.
Good, okay, good. So if there's a low number of side chains, then the object has high plasticity, okay? So what kind of relationship, how do we, yes?
As the amount of side chain increases, the plasticity decreases.
Okay, and so, yes, exactly. So what kind of relationship?
Indirect.
Indirect, okay? So let's write that on this side here, okay? This graph shows an indirect relationship between our number of side chains and the plasticity. Between the number of side chains and plasticity. Okay. So look at, there's a lot going on in this one graph, okay? And remember that side chains, remember the chains that are coming off the main branch, the main carbon branch here of this hydrocarbon. And so as we increase the side chains, okay, the plasticity decreases of this polymer, meaning it's less likely to be shaped or molded without breaking. It's going to break, okay, if it has a higher number of side chains, okay? All right, so folks, what I would like you to do is, you've got 1, 2, 3, 4, 5 more graphs on this. I would like you to do what we just did, so annotate these graphs, okay? You can go ahead and either work on your own or with the person next to you, and we're gonna talk about it in about 5 minutes. So define those words, tell me what the relationship is, okay?
What is the definition of density? I wasn't here for any of these, so.
Yeah, mass.
Explain what is going on in this text.
Mass per unit.
Yeah, mass per unit volume. And then what is it? Actually, indirect.
Hello.
Hello.
So what kind of relationship do we have here?
Indirect?
Yep, another indirect relationship, right? Between what two variables?
Is it the side chains density?
Mm-hmm. Good. So this is the one you tested. Do you remember testing this, Melissa, with the beakers? You dropped the pebbles in?
Yeah.
Okay. Be very specific. So don't just say this is an indirect or direct relationship. Tell me what it's a relationship between, okay?
I don't really care, to be honest.
All right, Ryan, I know you weren't here, so what do we got? We can do this even though you weren't here. So I gave you those definitions, right? That paper with the definitions on them? What'd you do with, okay, it'd be right, uh-oh.
Oh, I think I put them back here.
Yep, here they are. So there's plasticity, that's your first one. Your next one is density. Okay, so density is, this is the equation, this is how you could define it. Okay, so go ahead and write that for the definition. And then you can tell me, you can still tell me the relationship, right? Without, even though you weren't here?
Yeah.
Okay, so what kind of relationship is this?
So the more side chains, the less density.
Exactly, so it's another indirect relationship. Yep, you got it. Be careful when you get to the hardness test. Okay, that one's a little bit tricky. Hi, Liz. Yeah. Take about 2 to 3 more minutes. Good, guys? So just so you know, all the definitions are going to be right after the word, okay? You have all the definitions, or do you need another sheet? I can give it one back. Yep.
For this
So the all of them are right.
So like the longer the length, the
After, so there's your hardness one. Okay? How many of you are on the last page? You're doing the last few graphs. Okay, perfect.
what did you put for? 6.
Okay, folks, we're going to move on. So finish up your last graph there. And take a look for me at the graph that says the effective polymer length and hardness of the polymer. Okay, this is one of the trickier ones here. And go ahead and look to your neighbor and see if you agree on the trend that's happening between hardness and the length of the polymer. Make sure you agree with your neighbor. So look at their graph.
Yeah, everyone's confused because they're not looking at the short, medium, and long categories, right?
Different for how math.
We'll just start off with 0.
Yeah, remember we did
Yeah.
this one.
The longer ones had less of a depression.
Yeah, which simulated the shorter ones are longer. Yeah, because of this.
Mm-hmm.
Good morning.
The shorter one has more.
Well, because it's
Thank you.
It's
You'll
harder.
need this today, okay?
Yeah, more. Hardness.
All right, so folks, what in this graph, okay, what is going on? So, Joe, what did you guys have for the relationship? Indirect between what?
The length of the polymer chain and the hardness.
Okay, so indirect between the length of the polymer and the hardness, okay? So ladies and gentlemen, hardness, you need to pay close attention to the units here. Millimeters depressed. Who did the hardness test? Wasn't it you guys in the back there, Jillian? No, it was you guys, okay. So when you did the hardness test, Kayla, how did you test this?
Well, we did the, what is that thing called?
The plumb bob.
Yeah, the plumb bob. We dropped that onto our polymer and we measured a toothpick on how deep the drop was.
Right. So the deeper it went, would it be harder or softer?
Softer.
Softer, right. So notice here, the depression, so how deep it goes, is high for a short chain, right? And for a long chain, it's low. So it doesn't go very deep, right? In this case, there's almost no data here. Okay, but you see that it's decreasing. So what does this mean in the terms of the relationship? Well, the longer the chain, the harder the polymer is, right? So that's really a direct relationship. It's just that you're looking at the depression, how deep it is going inside. So it's indirect between how deep it goes and direct between the actual variable, the hardness itself, right? The longer the chain, the less deep the depression is. That means the harder that the polymer is. Okay, so maybe make an edit to that if you didn't have that correct. All right, so folks, now what I need you to do is look at your next document that you picked up today. It looks like this. Have your graphs and tables right next to it, so maybe lay it on your desk like this, so that way you can refer back to this text today when you're going through this document. All right. So this is the document you should have out in front of you. And let's read the instructions. It says, so this is where we're going to meet our objective for today, which, as a reminder, how to determine the approximate chemical structure of a polymer based on its physical characteristics. At each station, you're going to find a different polymer. So I have them in the back, and I'll bring them up front in a second to you. Your task is to draw the chemical structure of the polymer by synthesizing the data found in your graph packet, this guy here, and your experiments from the previous lesson. Synthesizing is an important word here. Okay, so if I'm going to synthesize something, if I'm going to synthesize information, what am I going to do with that information? I'm going to, create it on the right track there. I'm going to what do you think I'm going to do if I've got my information from my lab and my information from my graphs? I'm going to do what with it? Create or put it to what? Put it together, right, in one place, in one area. Okay? All right, so we're going to do a class example first. It says common name of the polymer. So here's the example we're going to use today. What is a common name of this plastic or polymer? Ruler. A ruler, right? Yep, so let's go ahead and write that down. And what is the use and functionality of a ruler? Well, you can use it for different things, right? But one thing, the most common thing we use it for is to do what?
Measure.
Take measurements or measure, right? So let's write that. Or make measurements. Right? And I can also use it to make straight lines, okay, whatever. So make sure you've got some kind of use and functionality of this ruler. Okay? All right. Let's scroll down a little bit. So now we need to determine, this ruler is a type of polymer made up of monomers. It's a plastic. Okay, so we're going to determine what the structure of this ruler looks like based on these characteristics, these vocab words that we learned in our last lesson. Okay, so the first thing we need to look at are the number of side chains or branches, and that has to do with the group in the back there. They tested that. So observations related to characteristics. Look at your graph. Look on page 1 of your graphs document. And so what are the two characteristics we took note on related to the polymer side chains? The first one is your group. What is the first one? Okay, the plasticity, right? And the second one you guys did is the what?
It's density.
Density, right. Okay. All right, so let's look at our definition for plasticity again on your graphs. Okay, the plasticity is and you guys wrote this down, okay, to be molded or shaped without breaking. Can I mold or shape this ruler? If I try to bend it and shape it, is it gonna do it for me, or is it gonna break?
Yeah.
So medium, short, or medium plasticity, low, or high plasticity?
Immediate.
Yeah.
What? Yes, you can't just say yes. Medium. Hey, so it does. It bends a little bit. Hey, I can shape it a little bit, but eventually it's going to be relatively easy to break, right? Okay, so let's put that medium to low plasticity for our observations. So the ruler has medium to low plasticity. Okay. All right, whoops, I forgot my S in there. There we go. All right, so if it has a medium to low plasticity, let's make a claim based on our graphs about the number of side chains. So let's say, look at your DV there, that's plasticity, okay? Does it have a lot of side chains, a little amount of, a few number of side chains, or somewhere in the middle?
Middle.
Based on that graph.
Middle.
Somewhere in the middle, okay? So claim the plastic has a medium number of side chains. Sorry, that's a little sloppy there. All right. There's one other test we know of that we can use for number of side chains, and that's the density, okay, which is what this group measured. The density of this ruler, I put right on the ruler for us, is 0.89 grams per milliliter. Well, you don't know if that's medium, low, or high unless you have some sort of range. So I'm going to tell you that the range of our density of our different polymers is going to be between 0.8 and 1.5. Okay, so this one is 0.89. So that's going to be also on the lower end, low medium end of the density. So we can write that for our observation. The ruler has a relatively, we could add relatively low density. So that confirms, that goes along with this claim. That's still, the data still exists, or still complements each other. We don't have contradictory data, okay? So then finally, the evidence connecting our observations to our text. This is where we want to refer back to our graph, okay? So in your case, you've got figure 1 shows that, and then you're going to tell me that relationship. So figure 1, okay, so look at your graph 1, that's figure 1. And then tell me, what does figure 1 show? And you guys already told me that earlier in the lesson. Figure 1 shows a what type of relationship between? Indirect. Right, indirect. So you're going to write that down. Refer exactly to that figure. Figure 1 shows what kind of relationship? Okay? Between what and what, though? Don't just tell me indirect shows an indirect relationship. Between what and what? Between
Side chains
side chains and
and plasticity.
plasticity. Right. Between the number of side chains and the plasticity. Exactly. Between what? Relationship between what? Be as specific as possible. Okay? Between what? Because if you say that for everyone, we don't know what you're talking about. We need to be very specific. Okay, we've got the first characteristic down. Now we need to know the number of crosslinks or bridges, okay, that this polymer has. So who did the crosslinks and bridges? I think it was you guys in the middle, right? And so how would you describe, Griffin, how would you, were you here for lab? How would you describe a bridge or cross-link?
It's like connecting. I don't know. Like how to
Connecting, yeah,
explain it.
connecting what?
Each part of the hydrocarbon.
Okay, right, connecting the hydrocarbons together, exactly. So when it says bridges or cross-links, so if here's one hydrocarbon, here's a second hydrocarbon and a third, the bridges or cross-links are going to connect the hydrocarbons together. Okay? So we want to know, does this polymer, does this plastic here have a large number of cross-links or a small number of cross-links? Well, what are our characteristics? You're going to have to turn the page on your graphs. And what are the two characteristics that will tell us about the bridges? One is, well,
Tensile strength?
tensile strength, which is what you tested, right?
No, we had a list.
Oh, you had elasticity?
tensile.
And you had tensile strength. Okay, Gio, what is tensile strength?
The force required to pull or rip something.
Right, and so how did you test that?
We put it in this clamp and then we pulled it with the weight.
Yep, with the different masses, and then you measured how much mass it took to break it, right?
Yeah.
And then you guys had elasticity, yes?
Yeah.
And how did you test that?
We had those two rubber balls.
Yep.
We had to bounce them.
So you did the height, right?
Yeah.
Okay, so what is the relationship here? Cross bridges. So does this, so you guys that did this lab, do you think I could add a lot of weight to this before it would break? Like if I could drill a little hole in here, which would take some effort, right? And then add weights, would it take a lot or little to break this?
A lot.
Probably a lot of weight to break this, right? So we could say the object has a high or a large amount of tensile strength, right? Because it would take a lot of weight. The ruler has a large amount tensile strength. So that's our first observation about the ruler. It's got a large amount of tensile strength because this group says they think it would take a lot of weight to pull it or break it. So the other part then is the elasticity. And so the elasticity we can measure by making something bounce. But it's also, if you look at the definition, return to its original shape. Okay? So does this object, does it want to return to the original shape when I twist and tug at it?
Yeah.
Yes.
Yes, it does. Okay? So the ruler has a large amount of elasticity as well. Okay? So we can write that for our second observation. Okay, so if it's got high elasticity, it's got high tensile strength. What does that mean about the cross-links in this polymer?
Oh,
Yep,
they're high.
they're high because now we have a different kind of relationship. We've got a direct relationship, right? So large number of cross-links is our claim. Large number of cross-links. And our evidence is going to be similar to our last one. You need to write down the graph or the figure number and what that shows. So figure 3 and figure 4, right? What do they show? What's the relationship between crosslinks and polymer? And strength or tensile strength or elasticity. Yes, direct relationship, right. So once you've got your claim, cite your evidence, which is right from your graphs, right from your figures. So tell me, what does figure 3 show? What does figure 4 show? And when you're ready, turn the page and we'll look at the last two together and then you're going to do your own. Okay, finally we've got the length of the chain. So that's what these two groups tested on lab day, how long or short the hydrocarbon is. Okay, so we've got two ways to measure that, the hardness and we've got the melting point. You guys did melting point, yes? Okay, so what is the relationship between the length and the melting point, Jillian?
The higher the length, the higher the melting point.
Okay, so the higher the length, the higher the melting point, good. Okay, so there's a direct relationship. And then hardness, that's the one they said where they measured it, where they dropped the bob into the plastic and then just how deep it went. What's the relationship there between the length and the hardness? This is the one that's a little tricky. The harder it is, the longer or shorter your plastic is. Shorter. Okay, your polymer. Okay, so the longer it is, the harder or softer, I'm sorry. Which one?
Harder.
Harder, right? Yes, harder. Okay? Okay, so so for this one, if we drop the bob into this ruler, do you think it would take make a big depression or small?
Small.
Probably a smaller depression, right? Okay, so the claim would be that the polymer is hard or soft if it's making a small depression.
Hard.
Hard, right, exactly. Okay, so the polymer is hard. Okay, so that's our observation, I'm sorry. That's our observation. The polymer appears hard. And I'm going to give you the melting point of this polymer. It's about 190 degrees Celsius. Okay, so pretty hot. Yes, our range of melting points of all our polymers will be between 60 and 200. So this is on the higher end of melting point. So if it's got a high melting point, what does that mean about our chain length? And it's longer or shorter? Long. Okay. So the observation is the melting point is high. I'm going to put MP for melting point. I'll put relatively high. Both of these observations correspond to the claim that we've got a long chain. Not chair, chain. And then again, please cite your evidence for this. Where do we get this information? What do those graphs show us? As you write your last piece there, folks, I'm going to pass out the polymers you're going to try and test out. Oops, sorry. Scooch that just a bit, Mel. Thank you. And maybe I'll put this up that side. Before you guys move on and you test your polymers, we got to make our final claim about what the polymer looks like chemically based on what we said. Okay, so first let's always start with the easiest one. I think it's the length of the chain. Do we have a long or short chain?
Long.
We have a longer chain, so let's fill this box up and draw a nice long hydrocarbon here. We're going to have to draw a couple because we need to show those bridges and the branches. So we've got a nice long chain. Did we have a lot of branches or medium number or few branches? What did we decide? Medium number of branches. All right. So coming off of our polymer, we've got to have some branches. So I'm going to go every couple because we have a medium number of branches. And then finally we had our cross links. Do we have many or few cross links? We had many, right?
Yeah.
Many cross links
Yeah.
Yes.
or bridges.
Yeah.
So then draw your cross links or bridges between your hydrocarbon chains, your central chains. Very nice. All right, guys, you see what we're doing today? Yes? No? Yes.
Yes.
Okay, good. So go ahead. You now have polymers. Turn your page. And if you have more than one polymer, write down the common names of those. You're going to notice that in your boxes, there's a density and melting point of these. Play around with them, okay, to decide on the structure of these polymers.
Ours is like, wait, what is this? Is this rubber? Yeah.
Yeah, it's a river.
It's just.
It's like
There you go. Melting point and stuff is in here, okay?
Alright, let's get it going. Which one do we want to do first?
We're gonna put this right here, so
It's just that I'm like regionally hormone right now, and I got
To the next page and get going, guys.
We could do that.
So you guys know what this is?
PCP.
Right, yep. PVC. There you go.
That's PCP.
And so what would I use PVC pipe for?
Piping.
Drinking
Yeah,
water.
what kind, yeah, okay.
Plumbing.
So you guys have candle, yes? So this isn't a type of plastic, it's a what? Yeah.
All right, number of side branches. Plasticity.
I agree. He looks tired.
Yep, you should have two, yep, and they're approximately the same for both, right, yep. It should be the lower one, okay, so sorry, yep, I have somehow maybe that got switched up. Yes. All right, so you don't have rubber, or plastic, you have rubber, yeah,
Okay.
which is still a type of polymer, it's just different,
Is that racing?
different structure.
Also, the race is rubber, right?
Yes, yeah. Yeah.
So like, what are we writing?
Okay, the functionality of
Sure,
this
why
is
don't
to
You,
the functionality of this
a
is
cylinder,
to
a
stop.
polymer
I'm pretty sure, yeah.
block, plastic block. It's actually, so it's I think it's 8 high density polyethylene. Yeah, it is. So if you want the name, it would be right in back here. So HDPE, or high density polyethylene. Okay, that would be your name for this. And that's not the common name of this. This is what? Yeah, well, right, Blondie returns your bottle, right? So HDP. Okay? Right, bleach alternative.
Bleach, so. Are you sure, am I right? Okay, so we'll do the weird block first. So HDPE.
The same thing with plywood, though.
And how do I feel about that? Because it's not a real
There's no trace
Break.
of plastic in here. I mean, this one I can, if you try really hard. You
So
use
folks,
something.
I'm less worried if you're
Elasticity.
exactly right than if you made some, if you have evidence to back up what you have.
Yes.
Right?
Okay, so
It's the measure of an object to be molded or shaped without breaking.
Staring at the TV the whole entire time.
It has many side chains, guys. Because it doesn't bend and the density over one bolt. Mr. Fox, what if I break this?
Don't break it.
With my finger, yeah, every time I would just like try that.
Don't do that.
Stare at the camera.
Careful. All right, guys, you need to make some. Come on, let's go. You're a little behind here. Everyone else has got at least one.
Come on.
Okay?
So we can't really stretch it, so.
Observation. Number of side chains.
The claim is it has many side chains.
How's your polymer look? Okay, so so it's a long polymer, yeah? Okay. With some side, or it looks like you have a lot of bridges, or medium amount of bridges?
Large. No. Yeah.
Okay. Here's what I want you to do.
Because it's stronger or
This last piece right here is gonna, so you're gonna skip this for now, we'll come back. Your plastic is one of these sticks. 1, 2, 3, 1, 2, 3, 4, 5, 6. Decide what it is, what the technical name of it is, and then, so you'll put the name of it here. Support the, use quotes that helps you support the name of it and some observations from today's experiment, or observations, okay? All right, sounds good, thank you. Can I take your polymer?
Got wet from the sneeze.
No. Yeah, I was trying to like this way.
Yeah, but I feel a little my knuckle.
Really gonna bounce. I don't know. No, I'm getting it.
Well, for the first one, we just say we have functional.
Wait, you have another day to do it. The PowerPoint.
Wait till the bell rings, okay, bud?
Yeah, I'm just putting it all in.
Bless you.
There goes Mr. Fox and Polly.
Make your third claim before we go here,
Yes,
okay?
sir. I got you, Mr. Fox.
All right, ladies and gentlemen, hold on. Don't pack up yet. Listen for my instructions. I know the bell's about to ring. We've got 2 minutes here. I want to make sure everyone knows what their assignment is because some of us didn't get to it. If you didn't draw your first polymer, can I use yours as an example, Maddie? Make sure you have this first one and this second one completed, okay? So Maddie's got a shorter polymer. Make sure you have that done because tomorrow we're gonna need to trade, and if you haven't all finished, okay, then we're not gonna be able to do that. The second thing you need to do tonight, folks, is there's some reading on the back. It tells you about the different polymers. Hold on, guys, wait. I need everyone to hear me. You need to make a claim about what type of polymer you observed today. There's technical names here like high density polyethylene, low density. What was your polymer? It's going to be one of these 6. Make a claim about what it was. Provide evidence from the text and some evidence from your observations today. Okay? I'm going to want to see that tomorrow. Have a wonderful day. Thank